Hey, nice grounding strap you've got there. Very stylish. Yeah, I get it. You're an engineer. Kudos to you for following good practice and wearing a grounding strap when you're working in the lab. But maybe for you, it's also some kind of a fashion statement. You wear it around just so folks think, hey, there goes an engineer. But if you're wearing it at home while unboxing that product you just designed, that might be a sign you didn't do all you needed to for ESD protection. So, are you planning on including a grounding strap in your product design, or maybe just a note to the customer saying the warranty is void if they don't wear one? Yeah, I didn't think so. Hi, I'm Amelia Dalton, host of Chalk Talk. We need to get this whole ESD protection thing figured out once and for all. So hang around for a few minutes while I bring in Tom Wolf from Nexperia. He's going to talk to us about how to choose the right protection for your circuit. And don't worry, you can still wear your grounding strap to the grocery store. Makes kind of a nice look with that slide rule belt clip. And before we get started, don't forget to click that link. There you can find even more information about the fundamentals of ESD and TVS protection from Nexperia. Hi, Tom. Thank you so much for joining me.
Hello, Amelia. Thank you for letting me be here.
Absolutely. So we're talking about the basics of ESD and TVS protection today. But Tom, before we get into the details here, what all will we be covering today?
We've got a nice agenda for you today. First, we want to look at ESD and TVS, just the basics. What is it? How do I recognize it? Then we'll go on to the selection criteria parameters. That means if you're selecting a part for ESD or TVS protection, what value should be looking at when you're selecting your device itself. And it's important to know protection topologies. We're going to have to talk about a couple things, unidirectional and bidirectional, and go through those because that's also part of the process. And then finally, at the end, I'm going to show you some specific part numbers and places to go for more information when you're selecting that ESD protection device.
Excellent. So, Tom, let's start with ESD or electrostatic discharge. What are we really talking about here?
Electrostatic discharge. Everybody actually knows it already. We call it the fuzzy slipper syndrome. You get up on a cold winter morning, it's dry out, you put on the fuzzy slippers, you shuffle across the carpet, you touch the doorknob, and zap, you see a spark there. That is ESD. You just touched the doorknob and you know what that felt like. Imagine if that's hitting a little small integrated circuit. That's what we're trying to protect against, ESD damaging that electronic device. So because of that, we've got several different models that we work with. For example, we talk about electricity of a charged person touching a integrated device itself. That's the fuzzy slipper syndrome right there. However, it could be that the IC device itself got charged. It's in the tube that it's shipped in, it's in the tape and reel. There's static energy on that. You take it out of the reel, drop it onto a metal table, and it's going to discharge into the table. That's a second type of ESD damage or event which could occur. A third one is a charged machine touches the device. When it's being assembled on the circuit board, the big pick-and-place machine, what happens if it has an ESD charge in it for whatever reason? It touches this poor lonely IC, bang, discharges into it as well. So anytime electrostatic energy can be stored up and then suddenly discharged into a device, that's exactly what we're trying to avoid. And the damage can be quite severe. We've got some photos here of it. The gate oxide on a device, that's the semiconductor insulator inside the part itself. It's only a couple of nanometers wide. So you can actually have the electricity punch right through it. It blows a hole right through the middle of the material itself and obviously damages the device. You can damage the metallization. That's the wire leads inside the part that connect one transistor to another, one component to another. You can actually blast them right out of the way and the metal, the wire is gone between the parts itself. Or you can actually damage the junction, the PN junction, the semiconductor device itself. Too much voltage will physically damage that. And the real issue is that semiconductor devices today, they're not getting more robust. They tend to be getting more and more sensitive because geometries get smaller each time. You know, we're talking about 7 nanometer and 3 nanometer and 2 nanometer processes. Those are way more delicate and more prone to ESD energy than any device ever was before.
Absolutely. Now, Tom, what about TVS? How does that compare to ESD?
TVS, or transient voltage suppression, is its evil twin brother, so to speak. They are both energy getting into the circuit in the wrong way at the wrong time. Now, some people even can say that they're exactly the same thing because you almost treat them the same way. But the difference between ESD and TVS is that ESD is a very high voltage for a very short period of time, like nanoseconds. A transient voltage suppression, a TVS event, is a not as high a voltage, but it occurs for a much longer period of time. So the effects are both bad. One of them tends to punch a hole through the oxide itself. It's like a bullet going straight through it. That would be an ESD event. A TVS event, because it's longer current, it tends to heat the part instead, so you see burn damage as opposed to a hole punched through the electronic. In both cases, you've damaged the device, however, but like I said, it's the energy that you have that you're trying to avoid. They both are thermal energy. Both of them are protected by absorbing that extra energy into a ESD or a TVS device, converting it to heat so that it's harmless, doesn't get into the electronic device you're protecting. Then you let that heat bleed off and you wait for the next event to occur.
Okay, that makes sense. Now, Tom, can we get back to ESD for a minute? What kind of standards are we talking about here? I would imagine that there are device standards as well as system standards for ESD protection. Is that right?
Exactly. You need to have standards for these so you can determine if your device or your system can manage the electrostatic event which might occur during its lifetime. And so remember those models we talked about before about how if a human touches something or the charged device touches something, we have models for each of those which are electrical equivalents or electrical simulations of what it would be like. So we have things like the HBM, the human body model, which is an electronic simulation of what the average human touching the average part is like. So it's a way of testing what happens if somebody touches my IC. We have machine models. This is if the machine touches the device and discharges into it. The opposite is the charge device model, the CDM. That is if a device itself is charged, like it just came out of the wrapper, drops on a desk and discharges. We also have something called a transmission line pulse, which is kind of replacing or updating the other three models because it's a little more reliable and more repeatable. But all of those are models, and the reason I bring them up is that you will see them in data sheets. It will say this part is protected by HBM to 3 kilovolts, so you know what model it was tested against. Now, these are just the testing parameters for a device itself. Once you put that device into a system, like you put an IC into the computer itself, now you want to do a system test on it. And there's other standards for that because it's not just the protection of the device. The IC is in there, it's mounted in a circuit board on a ground, it has ESD devices around it, it's in a plastic case that has epoxy resin and all these other materials on it. So you want to measure what is the impact of the system. That's really where that fuzzy slipper syndrome comes in. If I have my laptop and instead of touching the doorknob, I touch the connector on the back of my laptop, how much charge can that handle? Because it's not just the IC, it is the entire system now which must be protected against that particular event. So these are standards that we can use for judging, can my IC survive the ESD or TVS event, or can my entire system survive the entire event?
That's really interesting, Tom. So ESD can be pretty destructive, right? What does that look like?
Here's some actual photos of it. Now, on the left is a chart of what an ESD event looks like, and it's similar for ESD or TVS. Within a few nanoseconds, I get this massive voltage. And when I mean massive, I mean 30,000 volts. It could be huge amounts of electricity comes into it, and then it tapers off over a period of time. Like I said before, an ESD is a high spike with not much behind it. It goes away pretty quickly. A TVS event, maybe that spike's not as tall, but the pulse itself is much longer. So it's the energy under the curve we always talk about. So the energy is similar, it's just how it's delivered. Anyway, a high voltage spike tends to punch holes in that gate oxide, and there's the cross-sectional diagram of an average IC. It actually blows a hole right through that. Your insulator's gone, part doesn't work anymore. On the bottom is what happens for that high energy, that long amount of current for a long period of time. It's thermal energy. It physically melts the device inside. So what's interesting is from a failure analysis point of view, if your device fails, semiconductor manufacturers can get the microscope out, look at it, and go, that was probably ESD. We see small holes. Or, nope, things are burned away. It's probably TVS damage. So there's almost a signature of an ESD versus a TVS event and the things that it will do to an integrated circuit.
Okay, cool. Now, Tom, what about internal ESD protection? How does that compare?
Well, all semiconductor manufacturers have to provide some level of protection to the device because the device is going to be handled bare before it's soldered to anything when it's its most sensitive. So So virtually all devices have some ESD protection on board. Here's just a part I picked up randomly. It's a P-channel trench MOSFET, but you can see circled there ESD protection to 2 kilovolts. In other words, this part standing by itself can take a 2,000 volt event. So it has the ability of absorbing that much energy while it is alone. So it can survive by itself, but more than that, you better have external protection around it. An ESD diode external to it, or your packaging, your cabinetry, or your metal shielding, for example. But virtually all devices have some inherent shielding in them just so they can be handled during assembly and manufacturing.
So, Tom, we also need to think about external ESD protection, right? What all should we be thinking about here?
To select that external ESD protection, you need to know certain parameters, certain things you're trying to protect in a system. For example, the number of signal lines. You may just have one wire you're trying to protect, or you may have a whole array of them. Do you put it in a single protection device or multiple protection devices? That's an option, and there's pros and cons for each of those. The package, how much space do you have? If you're building something like an electronic wristwatch or building a cellular phone or a device like that, you don't have much room. Packaging may be a critical specification for your device. Then you talk about the electrical specifications, something called a reverse standoff voltage. We'll talk about it in a second. The ESD robustness, how big of a shock do I plan on giving to this system? Clamping voltage and dynamic resistance. These are all critical parameters you need to understand before you can select the proper device to protect your system in the way that you want to protect it.
Okay, so can we talk about that number of signal lines? How does that make a difference here?
Imagine your laptop again. It's got USB connectors and VGA and HDMI connectors on it. They're all more than one pin. Because of space and wire routing and signal integrity, I really want to keep all those lines the same as I can. So what I typically look at is a device which can cover all of those. Here's a USB port, for example. There are 6 signal lines that I want to protect on it. I could use 6 or more individual diodes, then I have to wire them and place them and make sure all the signal lengths are the same and the capacitance isn't too high. Or I could just select a single device that has all 6 channels in one package. In other words, it's a black box protection design. Put it in, you know your USB port is protected. So first thing, how many lines are you trying to protect and how many components do you want to put in to protect those lines?
Okay, that makes sense. So what about that working voltage?
That would be the VRWM, or the reverse working maximum voltage. And what that is the amount of voltage that your system wants to run at without being triggered. In other words, I want to run at this voltage, and ESD protection device, don't come in, don't do anything, stay away, be invisible. For example, in an automotive application, I might pick a device like the PESD 2IVN24. The 24 tells me that this part will not trigger. It will not think it's an ESD event until it gets above 24 volts. So I can run at 12 volts and get spikes of 14 and 16 and 18. Nothing happens. Goes above 24 volts. Now I'm into that range where I get to the breakdown voltage of the device, the VBR. VBR says at this point, trigger. This is a bad ESD event. Do something about it. And that will typically be a little bit higher. So we say the working voltage is the voltage where your system's going to run at. Got a 5 volt system? Pick a 5 volt VRWM. If you're working at 12 volts or 24 volts, pick a device for that so that it doesn't get bothered by the ESD device until you get above that particular voltage.
Okay, so another one of the criteria you mentioned was clamping voltage, right? Can we look at that one a little closer?
Exactly. Clamping voltage is the voltage which it protects you to. So I've got a diagram here. On the left is an input signal. You saw it a couple pages ago. This is a typical ESD or even a TVS strike. Now it may be 30,000 volts that comes in. You would ideally like to have your 24 volt device protected to 24 volts. The voltage never goes above 24. I hold it at exactly 24. Laws of physics say you can't do that. So in reality, when that 30,000 volt spike hits, in this case it's actually 8,000 volt spike, on the right side of the diagram you see the spike go up to several hundred volts and then it rings down. And then after a few nanoseconds you go, oh, that's where the clamping voltage is. Because like I said, it doesn't occur instantaneously. So the clamping voltage, it's critical to know how it was tested. Where is the point in time where you actually measure what is the clamping voltage? So for this example, again, it's a 8,000 volt spike into this particular 24 volt device, and we measure it at 30 nanoseconds. That is the standard where you happen to measure it at, and you could look at that point and say, yep, at 30 nanoseconds, we're at 24 volts. That is my clamping voltage.
Okay, so what about testing how robust your ESD protection is, Tom?
Well, this is what you really pick. This is how much protection your system wants. Now remember, my device itself is probably protected to a couple thousand volts, but suppose your laptop is going to be suspected to the fuzzy slipper syndrome. So I might want to protect it for 10,000 volts or 15,000 volts or 30,000 volts. That's what you pick. How bad is the environment where your system's going to be in, where the IC will see that energy, and then you pick the device on it. Just as a kind of a rule or a general reference here, 30,000 volts in air can jump about a centimeter, so about the width of a fingernail. So if you're trying to protect it against an event like that, that's 30,000 volts. Make sure that your ESD device is rated for robustness of a 30,000 volt strike. If it's more protected, maybe pick a slightly less voltage, a 15,000 volt part, may be more accurate for that application.
Okay, so the last criteria you mentioned was dynamic resistance, right?
Exactly. Now, dynamic resistance is the change in resistance of the part. When the device is sitting there monitoring for an ESD event, you want it to have infinite resistance. You want it to be invisible to the circuit. When an ESD event occurs, you want the resistance to go very low, very quickly, absorb all that energy, and then when it's over, you want the resistance to go way back up again so that the part becomes invisible. So this is actually a chart of voltage versus current. Since V equals IR, this is the resistance. The slope of that line tells me how fast that resistance comes online. If it's a very steep line, almost vertical, that means that resistance comes on almost immediately and absorbs that ESD or TVS energy. If it's a laying down line, almost horizontal, it means it's going to take a long time before that device comes in and begins protecting. So ideally, you want a pretty steep line on that dynamic resistance to turn on and absorb that ESD energy.
Okay, so Tom, for any kind of ESD protection, we also need to talk about protection topologies, right? Which topologies should we be looking at here?
The thing to remember about ESD energy is that you cannot block ESD energy. Remember, it's 30,000 volts. That can jump a centimeter. If your part's only a millimeter wide, ESD would just leap right over it and ignore it. Instead, what you want to do is provide a better path to ground. You want to divert that energy and say, hey, don't go into my IC I'm protecting. Instead, follow this nice, easy path to ground. And so there's multiple ways of providing that easy path to ground. You can use Zener devices, in which case there are unidirectional and bidirectional devices, and that determines on how they absorb positive energy spikes versus negative energy spikes. And then we have something called a snapback device, which is also known as an SCR device. That is another method of absorbing that energy. But again, they're all doing the same thing. Take the energy which would have caused damage and send it somewhere else. Send it to ground where it won't cause any trouble.
Okay, Tom, let's start with that first one. Zener diode unidirectional. What does that look like?
Unidirectional talks about what type of energy or what direction the energy is coming from. How do I absorb both positive flowing ESD energy and negative flowing ESD energy? Now, this uses a Zener diode. A Zener diode is a diode which begins to conduct at a known voltage. That's where that breakdown voltage and the VRWM come into it. So a negative ESD pulse will pass through the Zener diode in its forward bias mode. It says if you get above a certain voltage, conduct. So that negative energy has a way to get to ground successfully, and I've absorbed that energy. However, what happens if it is a positive ESD pulse? In that case, it's going to flow backwards through the diode, in which case the method that it gets conducted is when it gets to the avalanche mode of the device, which is a different voltage. So if you look at the chart, what you get is this asymmetrical response. How fast and how quickly I absorb the energy of a negative pulse versus a positive pulse is different. It's asymmetrical. It's good. It protects your system, but it may not be what you need for a very, very sensitive circuit. So because of that, we have other methods of doing it.
Okay, so I think the bidirectional Zener diode was next, right?
Correct. So the bidirectional is a much more symmetrical method. In this case, I've taken two Zener diodes and I've stuck them end to end inside. So whichever way the ESD pulse comes in, whether it's a negative pulse or a positive pulse, it's always being passed through that avalanche breakdown voltage. It's exactly the same voltage, exactly the same way it's diverted, regardless of which way the energy is coming in. So what I get is this nice symmetrical chart in the bottom. I know that whether it's positive or negative, I trap the energy, I divert it exactly the same way. So for a very sensitive circuit, you may want to go with a bidirectional as opposed to a unidirectional, but it's really up to your design application.
Ah, okay. So what about those snapback devices? I think that one was the last one on your list.
Exactly. A snapback device, or it's known in the industry as an SCR device or a trios device. The idea of it, though, is instead of using a actual physical Zener diode like the other two, we use something called an ideal diode, which is shown here in the upper left corner. It's a number of transistors and FETs inside. But essentially what it says is if you get above a minimal voltage, instead of just conducting like a diode would, slam this SCR in place. It's like a physical electrical switch which goes in there and shorts to the ground so that that ESD energy isn't passing through forward breakdown or reverse or anything like that. It's actually being shorted straight to ground. So what I get with that is something called a snapback effect. The voltage may go relatively high when it first comes in, and then a nanosecond later, because it takes a small amount of time for this SCR to turn on, the SCR shorts the line better than the Zener diode could. So it actually yanks the voltage back to a lower voltage, and then the dynamic goes from that point. So for really sensitive circuits where you're saying, look, my VBR and my VRWM are really close to each other, I don't want to play in that danger zone. I want to have this part trigger, pull the voltage way back to a safe level during the event itself, and then once the ESD event is over, release it and go back to normal operation. So this gives you the protection for the absolute most sensitive type of circuits.
Okay. So, Tom, what does Nexperia offer in terms of ESD and TVS protection?
Nexperia has a complete portfolio of all these devices. You can get individual diodes and design your own system. Even if it's multi-channels, maybe you want to lay it out your own way with your own special diodes. That option's available. Or you can buy a black box design, which is HDMI all in one place. All the pins, connections tested, ready to go to HDMI, USB. All of the automotive protocols are available, CAN and LIN and FlexRay. All those have standard blocks which are available, which will do all the work for you. Plug them in and you're protected up to the level which is required for that particular ESD event. We also have surge protection TVS devices. Remember, a TVS device is similar, but it's more of a thermal event. So these tend to be bigger devices, 400 watts, that they can absorb a huge amount of energy and then cool down in anticipation of the next event. We also have something which we didn't talk about today, common mode and EMI filtering. These are built for things like HDMI and USB 3.0 and some of the new standards where I want to reject common mode noise. In other words, what happens if the ESD event occurs on both lines simultaneously? Well, I have no reference. How do I know what's an event and what's a normal voltage? So this device actually has a solid state inductor on board, which absorbs that common mode noise as well too. So it's a way of protecting lines which would be difficult with standard ESD solutions. And again, like I said, there's automotive solutions as well too. All the automotive protocols, they have all standard devices as well. So whatever you're trying to protect from ESD or TVS events in whatever environment, there's a device which will do it.
Excellent. Okay. So what kind of part numbers are we talking about? How do we know what protection devices we want?
Well, we try to make it easy. Our ESD devices start with a PESD, so you know that that is the device, and also buried in that number will be the breakdown voltage, VRWM. A lot of information is included in the part number. A TVS diode is a PTVS. We try to make that one obvious as well too. And then the common mode parts, a PCMF, common mode filter device. So the part numbers sort of tell you, and the rest of the number tells you the voltages, the packages, and all the information for it. By the way, to get more information on this, as well as the other parameters and applications, the electrical specifications, we have available the ESD application handbook. You can either try to memorize that URL that's on the page or just go to the Nexperia website and ask for the ESD handbook and it will take you to it. You can download a PDF version of it and that will explain even in more details how to select that proper device for your particular ESD prediction.
That's great, Tom. Okay, so what are the biggest takeaways that you'd like my audience to know about our talk today?
So here's the summary on ESD and TVS protection. First, you need to understand the fundamentals. What is the ESD event? What is a TVS event? What can it do to your system? Based on that, understand the parameters are needed. How much VRWM does your system need? What breakdown can it tolerate? How many channels do you have? What are the parameters you're trying to protect in your system? Then how much protection do you need? Remember, there's the protection of the IC device itself, but there's a whole system around it. So it's kind of a compromise. Maybe I'll take a little bit out here and I'll put a little bit more into the packaging of the device and the metal shielding in the laptop itself. So that's where you decide what does the IC, what does the circuit board, and what does each point in the system, how much protection does it need? Decide on that, and then you're ready to select the proper device from our portfolio. Go to our parametric search engine, tell it the values you need, and it will quickly give you the value to say, this is the device you need to protect your system from ESD and TVS events.
Excellent. Well, I think that's all I have time for today. This has been super helpful. Thank you so much for joining me, Tom.
Thank you, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find even more information about the fundamentals of ESD and TVS protection from Nexperia. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.